For the second lecture in our physics module, we're going to apply some of the fundamentals and foundations we went over in the last lecture, as it pertains to motion. Before we can even talk about motion, we must first address what position is. In physics, there are two ways to address position. One is displacement, which is the change in position in space that doesn't account for path taken. This is a vector quantity from start point to end point. Distance, on the other hand, considers the path taken by the object, and it's a scalar quantity. To address the distinction between the two, let's look at a system. If I were to take a path like so, with each taking 2 kilometers of distance, my displacement would be 0 because I ended where I started. However, my distance would be 2 times 4, which would be 8 kilometers total. Make sure you understand these distinctions on test day. They are not the same thing. Make sure that you don't get them mixed up. Now that we've talked about position, let's talk about velocity. Velocity, quite simply, is the rate of change of displacement over time. It's a vector quantity. Average speed, on the other hand, pertains to the distance traveled divided by the total time. Average speed and average velocity are not the same thing. Average velocity takes into account total displacement, whereas speed takes into account distance. Make sure you understand these differences. Instantaneous velocity, on the other hand, is a limit. Don't worry too much about this, but for a more conceptual understanding, it might help you to study this. Instantaneous speed is the magnitude of the instantaneous velocity vector. Now that we've covered velocity, let's talk about acceleration. This is defined as a rate of change of velocity over time. Deceleration, as it sounds, is acceleration in the opposite direction of initial velocity. Acceleration is where the change is in the same direction as initial velocity. On a graph, note that for a graph of velocity versus time at any point, the tangent is the acceleration. A negative slope is a deceleration, and a positive slope is an acceleration. So if we were to draw out a graph real quick, with time and velocity, and it were to look something like this. If we were to look at this point right here, and we were to look at the tangent, this would have a positive slope. Therefore, it's an acceleration. However, on this side, if we were to take this into account, it would have a negative slope. Therefore, it would be a deceleration. On test day, you may have a graph like this, so make sure you know how to read them. We've gone over the basic three: acceleration, velocity, and position. Let's go into some other concepts now. The first we'll go into is friction. Friction is a force that opposes any type of movement, and it's comprised of either static or kinetic friction. Static friction exists between a stationary object and the surface it rests on. The coefficient is dependent on the two materials in contact. There is also a normal force between these two perpendicular to the plane. The coefficient of static friction, however, will always be greater than that of kinetic friction. The reasoning for this, from a day-to-day standpoint, if you were to try to push an object, you'll notice that once you get it into motion, it's easier to keep it in motion than it was when you started. Kinetic friction exists between a sliding object and the surface it slides over. Note that for both of these equations, you have a mu constant, which is the coefficient of friction, and n, which is the normal force. If I were to draw a block in motion, if it's moving this way with some force, the force of friction would be in the opposite direction. Here's a little fun fact for you, but have you ever thought about why a wheel works? If you think it's because the rolling moves you forward, you'd be thinking wrong. The reason why a wheel works is because the force of friction carries you forward, not the rolling of the tire. We've gone over some concepts now, and a couple basics when it comes to motion. Let's go into the application of these concepts. Note, on the MCAT, you will only have to deal with motion with constant acceleration. Anything where a variable acceleration is required is beyond the scope of the test. Linear motion is the simplest and most straightforward of the types of motion. It states that the object's velocity and acceleration are along the line of motion. Note that acceleration and velocity don't have to be pointing in the same direction. It just has to be going along the same plane. Here are some relevant equations. Note v naught is initial, a is acceleration, t is time, x is position, and v average is, well, the average velocity. Make sure you have a good handle on these equations and know how to use them come test day. When it comes to motion, a very classic example that you may see on the test is that of falling objects. This is a constant acceleration because falling objects are susceptible to the gravity of their environment. It takes air resistance into account unless otherwise prompted on the test. One situation that I would recommend you commit to memory is terminal velocity, which is when the drag force equals the magnitude of the weight of the object. Projectile motion. This is motion that follows along a path that's two-dimensional. For the MCAT purpose, you can generally assume that there's no air resistance, so the horizontal velocity will be constant. Trig identities and relations will be needed to assign these component values. This is something we covered in the previous lecture, so you should be very proficient at these by now. Just remember that for a vertical component, y, you need to use sine functions. For a horizontal component, x, you need to use cosine. Examples of projectile motion include throwing balls, cannons, and other sorts of motions that go along a parabolic path. Inclined planes. This is a very, very, very classic example that you will see on test day. It's a motion along two dimensions just like projectile motion. However, you will have to adjust based on the system. So if I were to draw something out for you. So here we have an incline with some angle theta, and we're to have a block resting on it. How might we assign our force of gravity and our normal force in terms of a free body diagram? Well, the normal force would go straight up like so. However, the force of gravity would point straight down. Draw that arrow just a little better. How might we adjust this for a more easy calculation? Well, if I were to draw my system again with my block, I could adjust it such that normal force runs along this axis. I could state that there is a force perpendicular and a force parallel. This may make our calculations a little bit easier because we take our force of gravity and adjust it accordingly. So I can convert a system that's at an incline into something that's a little bit more manageable. Another example of motion with constant acceleration is circular motion. It's an instantaneous velocity vector that is always tangent to the circular path. It's kept in this path by a centripetal force which is pointed inwards radially. The centripetal acceleration is the acceleration that's generated by the centripetal force. Any object that no longer has the centripetal force will deviate from this path. And below is an equation to help you calculate circular motion. It's a description of the path taken. Note, I'm sure you've heard of centrifugal force before. This is not the same thing as centripetal force. Centrifugal force has to do with the force generated on substances in a centrifuge, which, for you lab geeks, you've probably used before. If I were to draw out a circular motion system, it would look something like this. So if I had some radius r, the object would be going along a path v, and the centripetal force would be pointing in, like so. Now that we've talked about a couple examples of motion with constant acceleration, let's talk about mechanical equilibrium. Before we can even talk about mechanical equilibrium, we need to talk about what a free body diagram is. It's a representation of forces acting in a system. You need to know how to set these up for test day. Examples of free body diagrams are for a hanging object, so if I had something that was dangling on a rope, I would have a tension and a force of gravity. This can get more complicated over time, obviously. So if I were to have an example like so, of something that was on a pulley with a weight, I would have a force of gravity and a tension. Also here, I could also state that I have a tension force, which is pulling the object down this way, and a force of friction. This is not technically in equilibrium per se. However, this is just one example of a free body diagram. Knowing how to set these up and having a good understanding of your three laws, you will be able to calculate most equilibrium equations that come test day. The first type of equilibrium we'll go into is translational equilibrium. This occurs when objects are moving without rotation and they are linear by nature. They only exist when the vector sum of all forces acting on an object is zero, such that it is a reiteration of Newton's first law. Pulleys, hanging weights, etc. are good examples of this. So, like I drew in the previous slide, if I had a weight that was being held up by a rope, this would be an example of a translational equilibrium. Another example that's a little bit more complicated is if I were to have an object that was being pulled in multiple directions. If all these forces net to zero, then this object would technically be in equilibrium. The last type of equilibrium we'll talk about is rotational equilibrium. This occurs when forces are applied on an object in a way that the object rotates along a fixed pivot point, or a fulcrum. Torque exists when torque is the equation of interest here, and it's the application of force at some distance away from the fulcrum. This is calculated via cross product, which you should remember from the previous lecture. Note that an object in rotational equilibrium can only be so if the vector sum of all torques acting on the object is zero. So an example would be a seesaw or a spinning object. So a seesaw is a very classic example, like so. If it's not moving and it's perfectly balanced, we would say that this is in rotational equilibrium. For these calculations, make sure you have a good grasp of cross products, because torque, as you can see, is basically a cross product. Now that we've covered some foundations and a couple examples of motion, we will continue on with our physics unit. Keep these in mind. Kinematics and dynamics are very important for most physics calculations. Without a good grasp of these concepts, you will not be able to proceed much further. So that'll do it for our second lecture in the series. Join us next time as we move into some work and energy.